this was, you know, I know it's not a conical pendulum, but we're still going through the same kinds of things. We have drawn a diagram, right? I've put on the physical forces that are there. What do I do next? I did step 1, which is draw. Step 2 is trig and geometry, so that I can work out, like this thing, when I get towards resolving its forces, which way is everything facing, okay? So what I'm going to do is I'm just going to take part of this diagram, this part where the forces are, draw that out separately so that I can understand it a little better. Okay, so there's the normal force, right? Now, which way are all of the forces and all their magnitudes going when I start to resolve this thing, okay? So if you've got some colors there, you can see there's a horizontal component, like this. And you can see, importantly, that this horizontal component of the normal force, it's centripetal. It's headed towards O. So that's good. That's what we want it to do, right? So I'll work out what that is in a second. And then you've got the vertical component, which is heading up like you would expect. All right, so have a look with me. What angles can we use in here? What can we take advantage of? So there's some parallel lines, there's some alternate angles. If you do your work, I'm pretty sure you should find, you know, up here you'll have theta, alternate angles. And because this is the normal, right? That means that these two are complementary. So I've got 90 minus theta there. Is that all right? 90 minus theta, 90. That means that theta is up in this corner. Is that all right? Okay. By the same alternate angles, you can see theta will be over here. Okay. And that's all you need to work out what the magnitudes of all the forces are. Okay. For instance, the vertical one, right? You've got adjacent and you've got hypotenuse. We've seen this a few times before, right? You're starting to get the hang of it. This is clearly going to be n cos theta, right? And conversely, you'll have n sine theta in the horizontal direction. So now I've resolved everything. Now I can put it in terms of vertical and horizontal and say, well, vertically I don't want to be going up and down, or horizontally I'm going in this circle, right? So vertically, you've got n cos theta going up and you've got mg going down, right? And those should be equal to each other, right? So n cos theta equals mg. Nothing too dramatic there. What's happening horizontally? You've only got a single force acting horizontally at the moment anyway, okay? So you've got n sine theta, and it's going towards the center. So that should be equal to, now, we're used to writing mr omega squared first, right? But being that this is bank tracks and we're kind of thinking more about cars, right? We're not usually driving around like, oh wow, I'm taking this corner at, you know, pi on 3 radians per second. So probably, rather than mr omega squared, we'll do m v squared on r. Okay, I think that makes more sense. Okay, because we will know linear velocity. Now, this is in an ideal world, okay? We're going around and the only forces acting are exactly balancing each other out. You'll see shortly what happens when that is not the case, okay? But I want to work out, well, what is that speed at which I should take this corner, okay? So how am I going to work this out? I've got v squared there. That's what I want to work out. Okay, so if I call this 1 and call this 2, which way should I go? And what should I do? Should I add, subtract? Any takers? What's the cleanest way to get to v squared and a nice simple sort of equation just for v squared, and then hence v? I think we should divide, shouldn't we? Right? Because that'll get rid of the n's, it'll get rid of the m's, and you can, if we do it this way, you'll just get tan theta, right? Which will be useful for its own thing. Okay, so if I divide, sorry, I should have said 2 divided by 1. N's will cancel, you'll just get that. M's will also cancel. What am I going to get? V squared on GR. Is that right? So now, if I just rearrange this a little bit, V squared equals GR tan theta. Okay, put a box around that. Put a box around this, because what this tells you is the optimum speed to take this turn. This is the optimum, or velocity, speed. It's all squared, so it doesn't matter in this case. Okay? This is the optimum speed given the radius of the road, or the curve of the road, and whatever angle you're embanked at. Okay? Now, that's fine. That's good. But that's sort of assuming the road's already there. Like, it has a given radius, it's going to go that far, and you can measure how the angle is, right? If I were a road designer, okay, I actually am in the position where I get to decide what these are based on this, right? So I'm looking at this from a very different point of view, okay? I'm making the road, and I'm thinking, how far should I embank this, okay? Because I can, I can put whatever amount of dirt and concrete and stuff to make this kind of height, okay? So how will I do this? It's a bit of a fancy algebraic trick. Remember I told you this diagram is actually way off scale, right? This angle theta is not really going to be that high. And when you think about it, like, you think about the roads that you've traveled on, and if you've been on a highway and you've seen turns like this, there will be very, very gentle inclines, right, in order to take these curves, okay? So in other words, you have small values of theta. Okay? Now, one of the things that you might remember from when you first did the trigonometry of, the calculus of trigonometric functions, right, is that tan theta, right, and sine theta are very close together for small values of theta, right? Because they look like, I'll just use this empty space in here. Here's sine, and then here is tan, and then, well, it's gone too far. There's that asymptote of pi on 2, right? So in here, they're pretty much the same thing, or the difference between them is negligible, okay? So I can say sine theta is going to be roughly equal to tan theta. Is that all right? Okay, now what I'm going to do is I'm going to substitute that into this line. Maybe I'll call this 3 so I can do this, okay? So I'm going to sub into 3. So instead of tan theta over here, I'm going to say that's sine theta, and it's roughly equal to v squared on gr. Close enough, okay? And the reason why this is useful, the reason why I would go to sine theta, is because I know what sine theta is in terms of these distances here, right? This hypotenuse is d, and this opposite side to the angle is h. That's what I'm trying to find, right? So this is really equal to opposite on hypotenuse. See that? Okay, now if I'm the road designer and I want to work out how high should I make this embankment, right? I just have to multiply d across, and then look at what we've got here. Okay, before we had optimum speed. That's if the road's already there and it already has a given radius and a given angle. Okay, but if you are in the opposite position, you're like, I can decide what I want the road to be. Then this line will give you the optimum height of the embankment, okay? Now notice what it depends on. It depends on, let's go from the bottom. It depends on r, right? That's the radius of this road. That's probably going to be decided for you, right? The council's like, look, this is where the road has to go, so they provide that to you. Depends on gravity, constant. Depends on d, what was d again? That's the road width, isn't it? Again, that's decided for you. It's like, okay, well look, we need 3 lanes for this highway, or it's 1 lane or whatever, okay? Now the final piece is v squared, right? So it's like, look, if you know where your road has to be, how wide, you know gravity, and then if you know a required speed, or if you want a particular optimum speed, like say, oh, I don't know, a speed limit, right? You say, look, this is on a highway. People should be taking this curve at 110 kilometers per hour, right? Instead of being in this position where you're the driver and you're like, how fast should I go? You're in this position, you say, look, I know how fast they should go. And so I'm going to substitute that into here and get a height out. Does that make sense? Okay. So this is all in an ideal world. Where everything is optimized and everything is nice and perfect, right? Optimum speed, optimum height for everything. But we don't live in an ideal world, do we? People take corners at all different speeds. people have cars of all different masses, okay? So what's going to happen is, for instance, suppose there's this corner here, right? And I'm just a little bit more reckless than you. So I'm like, okay, speed limit's 110. I just go ahead and I take it at 110. But everyone else, all the normal people, they're like, look at how tight that curve is, right? So people come in and they slow down. They approach it at maybe 90 kilometers an hour, okay? Or maybe you have like a really heavy car, okay? So when you have a heavy car, there's going to be more forces acting in this direction and this direction, right? And I've got a light car, so it's gonna go. So we have to account for all of these things, okay? So this is an ideal world. You can rule all that off. We're gonna draw a new diagram for a non-ideal world, okay? And I need more space.